Hi, my name is Lian, and this is an introduction to the paper on the asymptotic enumerativity property for Fano manifolds, written jointly with my co-authors Roya Beheshti, Lehmann, Riedl, Starr and Sho Tanimoto. This paper is concerned with a certain class of Gromov-Witten invariants, namely the fixed domain Gromov-Witten invariants. These are by definition virtual counts of stable maps from a nodal curve C tilde to a smooth projective variety X, which on the one hand satisfy the property that the stable contraction of C tilde is isomorphic to a given smooth curve C with fixed complex structure. And on the other hand, that F satisfy the maximal possible number of incidence conditions of the form F of a marked point on C tilde is equal to a fixed point on X. Now these invariants are defined by virtual integrals on the moduli space of stable maps, and have appeared in the literature since the 1990s in work on Waffa and Trillator formulas. They also appear under the name virtual Tevlev degrees in the literature of the last few years. Now the central question of this paper is whether these Gromov-Witten invariants are in fact enumerative. So what does this mean? By definition, these invariants count, in principle, smooth curves on a target variety X that look like this, passing through some collection of points. But also, in principle, mildly singular curves that look like this. So here I have a smooth curve attached to a union of rational tails that also passes through a collection of points on X. So the question is whether, in the calculation of these invariants, contributions from singular curves that look like this actually appear, or if in fact these invariants only count smooth curves on X, like in the picture on the left. Now, as is typical in Gromov-Witten theory, not all of these invariants are enumerative, so it can happen that singular contributions of this type appear. But it was observed in many cases of interest that the failure of enumerativity is relatively mild. So specifically, various X satisfy the property of asymptotic enumerativity. So this means that once the number of points that F is required to pass through becomes sufficiently large, or equivalently, the degree of these curves becomes sufficiently large, then contributions of this type go away, and these fixed domain Gromov-Witten invariants indeed only enumerate smooth curves on X, like these. And so some examples of X for which this property was previously known were Grossmanians, going back to the 1990s, as well as Del Pezzo surfaces and certain low-degree hypersurfaces in projected space. Now, it was speculated in work with Panter and Pandey from 2021 that in fact any Fano manifold X satisfies this property of asymptotic enumerativity. So one can view this as kind of the minimal positivity that one should impose on X for such a statement to be plausible. And one can also think that, well, once the degrees of these curves become sufficiently large, and if the stabilized domains of these curves are sufficiently general, then one has some hope to avoid the most pathological subvarieties of the moduli space of stable maps, and in particular avoid seeing contributions like this. So that's kind of the heuristic that motivates this recognition. Now I should mention that the question of deciding asymptotic enumerativity for a given target variety X is somewhat orthogonal to the usual methods of Gromov-Witten theory. Whereas Gromov-Witten theory is exclusively concerned with virtual integrals, the question of enumerativity is really a geometric one. It boils down to bounding the extent to which singular curves on X like these can deform in families of larger than expected dimension. And this is really a purely geometric question. So I'll now move to some of the new results from this paper. So in this paper we find many new examples of Fano manifolds that satisfy this property of asymptotic enumerativity. So for example, if X is a Fano threefold without anti-canonical lines, so without curves of the smallest possible anti-canonical degree, then X satisfies asymptotic enumerativity. And we also verify the asymptotic enumerativity property in a number of new families of hypersurfaces. So for example, general hypersurfaces in Pn of degree at most n minus 2, and arbitrary hypersurfaces in Pn of degree less than about a third the dimension. So these results go through some fairly non-trivial input about rational curves on these kinds of ranks. On the other hand of this paper, we also give some negative results, and in particular produce the first counterexamples to the speculation of planetary planning. So some examples of Fano manifolds that fail to satisfy the asymptotic enumerativity property are certain projective bundles over projective spaces, such as this Fano threefold, a P1 bundle over P2, that contains anti-canonical lines, and certain special hypersurfaces of degree at least half the dimension, in particular Fermat hypersurfaces. So I should mention there's still a range between a third the dimension of the hypersurface and half the dimension of the hypersurface, where it's unknown whether all hypersurfaces satisfy the asymptotic enumerativity property. Thanks for your attention, and we hope you enjoy reading the paper.